Okay, here in Module 4b, we're going to take a look at confidence intervals for population proportions as opposed to population means. We're going to take a look at why the calculations differ for computing a confidence interval about a proportion versus a confidence interval about a mean of the sample. And we're going to take a look at how to calculate and interpret these confidence intervals for a proportion. We're also going to describe what is meant by the margin of error when you watch, if you watch the news or read a newspaper or something, you'll often hear polls referred to as something like 45% approve of something with a 3% margin of error. So what is that margin of error about? Okay, so here we're going to take a look at a binary variable that is a variable that can only take on two possible values, either 1 or 0. So for example, we could ask people, do you shop online? And if a person answers, yes, I shop online, that person is scored a 1. If another person says, no, I don't shop online, that person scores a 0. And if we interview, if we survey, 1,000 people, we're going to get some proportion of those people, maybe 80%, let's say nowadays, that do shop online and 20% that don't shop online. COVID-19 drove an awful lot of people who had not previously shopped online to start doing some shopping online. So the proportion of people who do a little bit of shopping online nowadays, at least in the US, is pretty high. Or, 1 if a certain part is defective, 0 otherwise. 1 if you approve of Joe Biden's performance as president, and 0 if you don't. And we can ask questions about the proportion of people who shop online, the proportion of parts that are defective, the proportion of people who approve of Biden. The proportion, you can also just think of that as a fraction between 0 and 1. So what fraction of people shop online? What fraction of parts are defective? What fraction of people support Biden? Now, in this case, the mean of the sample is going to be the same as the proportion of the sample. This is because the only two possible values that the random variable might have are 1 or 0. In this case, the probability that the value of the random variable is 1 is simply the proportion. The probability that the random variable is 0 is the probability of the complement, which of course is 1 minus the proportion. The expected value of the random variable is the mean. I mean, that's what the expected value of a random variable is defined to be, and that simply works out to be the proportion, okay? Using the law of total probability, we can break that down and compute. Okay, 1 is one of the possible values, and it occurs proportion p of the time. 0 is the other possible value. It occurs 1 minus p of the time, and consequently the expected value is the mean, which is the proportion. And then similarly, we can compute the variance of this random variable, this binary variable. It is simply the 1 minus the mean squared times the probability of 1 plus 0 minus the mean squared times 1 minus p. And if you just grind that through algebraically, you get this thing that we've seen before about binomial variables, which is that the variance is p times 1 minus p. Notice an important thing here, which is that for this binary variable, we only have to calculate the proportion of the random variable having a value of 1. And the proportion not only tells us the mean, but also tells us the variance directly. We don't have to do, I mean, we can, here we did mechanically do the sort of long-winded form of the variance calculation, but we discover that the variance is completely determined by the proportion of ones. It's not a separate calculation like it is for an arbitrary distribution. All right, so what do we do with all this? Let me first point out that because the variance is p times 1 minus p, therefore the standard deviation is the square root of p times 1 minus p. In August, Reuters sponsored a poll. They sampled 1,000 adults, and 46% of the respondents had a favorable opinion of President Biden's performance. So, what can we conclude about this proportion of all 300 million adult residents of the U.S.? What can we what conclusion can we arrive about the favorability level for Biden among all of adults in the U.S. from this sample of 1,000 people? Okay, now the poll reported a margin of error of 3.1%. All right, so the poll is indicating that, all right, of these 1,000 people that we sampled, 46% or 0.46 had a favorable rating, plus or minus 3.1%. Okay, well, the sample mean, which gives us the proportion, is simply the sum of all the individual respondents' values, either 1 for approval or 0 for disapproval, divided by the number of people that we sampled from. All right? So that gives us the proportion. And because this is a sample proportion, we're not going to call it just plain P. P is the true population proportion. We use this notation P hat to indicate that this is a sample proportion. Why do we use hat? This is just one of these conventions that statisticians follow. Is X bar is sort of a special case, understood to mean the mean of some sample, and the mean of the sample is an estimator of the true mean of the population. For most other variables that are estimators of things, statisticians tend to put a hat on top to indicate or to differentiate between the sample versus the population. So p hat is the sample standard deviation, whereas just plain p is the true population standard deviation. Okay, well, because we have sampled well over 30 people, then the central limit theorem tells us that these sample proportions are going to be normally distributed with a mean of p and a standard deviation of square root p 1 minus p over n. Okay, the usual central limit theorem thing. And because of the central limit theorem being appropriate here, we know that there is a 95% chance that this p hat that we computed is within plus or minus 1.96 times the standard deviation. All right, 1.96 is our familiar 95% z-score from the standard normal distribution. And so this first probability relation here, the p hat is between p minus 1.96 times the standard deviation and p plus 1.96 times the standard deviation with a 95% confidence level. That's just the central limit theorem using p and p hat rather than mu and sigma. And we've also seen that just because of applying algebra, this also implies that the true population proportion is between our sample proportion minus 1.96 times the sample standard deviation and the sample proportion plus 1.96 times the sample standard deviation. All right, so that's also a 95% confidence level. All right, now if we plug in actual numbers to this equation, okay, we have our z-score is 1.96, our population, our sample population proportion is 0.46, which means that the proportion who do not approve of Biden is 0.54. Our sample size is 1,000. We calculate this so-called margin of error. This is where the term margin of error comes from. It's the size of the error bound. And here we just plug in numbers and we get 3.1%. So that is what the margin of error in a survey means. And I want to be careful to point out here that when you read a poll saying that the proportion of such and so is, X percent with a margin of error of Y percent, what they're not telling you, what is implicit in this description, is that we're talking about a 0.95 confidence interval. All right, so this is not being explicitly stated as part of the poll results, but it is implicitly understood by statisticians that this margin of error is assuming a 95% confidence interval. Somebody asked me during the first week, don't we use 5% as our alpha when we do these confidence intervals? And yes, by convention, for many, many, many things, people use 5%. Why do people use 5%? Well, because the lady drinking tea experiment used 5%. It's just this kind of long tradition of people using 5%, and there are circumstances where that's really not particularly appropriate. But in a poll, when you see this term margin of error, you should understand that that is the error interval at a 95% confidence level. Okay. And step 3 is we're just plugging in these numbers to get 0.46 or 46%, plus or minus 3.1%. All right. Well, so we surveyed 1,000 people out of the 300 million adults in the U.S., and we came to this conclusion that with a 95% level of confidence, the proportion of people who approve is 46%, plus or minus 3.1%. Now, what if we wanted a much smaller margin of error? Well, to obtain a smaller margin of error, we would have to crank up our sample size. In other words, instead of having our level of confidence times the proportion standard deviation be, instead of plugging in the sample values that we get to get the margin of error, we can instead specify our margin of error and compute backwards what n has to be in order to achieve that margin of error. All right, so we do a calculation that we've done before. We just multiply and divide and square various things to conclude that if we wanted a 1% margin of error, we would need to survey approximately 9,543. So in round terms, we would need to survey 10,000 people to move that margin of error down to 1% or below. Not only, I want to be clear about something here. Not only do we need to increase the size of our sample, but for both sample sizes, for any sample size, we need to be extremely, extremely, extremely careful that we are making a truly random sample. There are famous examples of polls that turn out to be incorrect. And it's usually because the sample was not actually randomly chosen. There was a bias in the sampling that led to a bad prediction. What if you have no idea about the proportion? What should you assume then in order to decide how many people you need to sample from, or how many parts you need to sample from, or whatever it is that you're sampling from? Well, it turns out if you simply plot this function, square root of p times 1 minus p, its maximum value occurs at 0.5. So when in doubt, if you have no idea what the true population is, and you want to generate a conservative estimate of what your sample size should be, just plug in a proportion of 0.5 and use that in your calculation here to figure out a conservative sample size. Now, so you may have noticed how surprisingly few people we had to sample in order to get this roughly 3% margin of error. We've got 300 million people in the U.S. We only had to sample 1,000, assuming that we really did that correctly randomly, to get a proportion estimate within plus or minus 3%. Again, assuming a 95% level of confidence, which in the newspaper we don't bother to report. Okay. Okay. Another thing that we did here that I didn't emphasize, but I will now, is notice that we are using a z-score here for our confidence interval rather than a t-score. Why is that? Well, the reason that we use the z-score rather than the t-score is that the standard deviation is determined by the proportion that we got from the sample. We don't have to do a separate calculation to compute this standard deviation. Therefore, there is no notion about degrees of freedom to worry about, and so we just use a straight z-score. Now, we know that for a small sample size, the central limit theorem is not going to hold, and we had a rule of thumb that we talked about earlier that your sample size should be at least 30. And I expressed a little reservation about that. Why did I express some reservation about that? Okay. You can have bias in your sample. And my prejudice is that the larger your sample size, on average, the less biased you are likely to be. Now that's not necessarily the case. That's not necessarily the case. There are famous instances where even a large sample size resulted in bad predictions, and we'll talk about some of those. But the analogous rule here for proportions is that your sample size times the proportion should be greater than 15. And also, the sample size times 1 minus the proportion, the complement of the proportion should also be greater than 15. So both of these rules should hold in order for your sample size to be appropriate. How does this relate to our rule about having a sample size of 30? Well, think about it. If the proportion is exactly 0.5, then the implication here is that n is 30 in order for n times 0.5 to be 15 or greater. Similarly for 1 minus p. So there is so these 15s are not just plucked out of thin air. They are related to the rule of thumb about 30 that we talked about before. ISLE, by the way, unfortunately does not have a confidence interval widget built into it for proportions. Okay, now, if we are lucky enough to have honest-to-goodness population data, like our Cobb County water usage data, then we've seen that doing random sampling can allow you to do good statistical inferences, making decisions about or arriving at conclusions about what the mean and standard deviation is for the water usage. Now, in real life, and particularly where humans are involved, random sampling is not easy at all, okay? Because when you are doing surveys of people, there are all kinds of human factors that can get in your way. You may have had the experience of being contacted by phone or by email and asked to participate in a survey. Did you choose to participate? Very likely not. I personally, when I get a phone call from some number I don't recognize, I typically will answer the phone, and it only takes me a few seconds to figure out whether it's somebody trying to sell me something, whether it's someone trying to get me to give money to a cause or a politician. The minute I discover that this is a call from someone that I didn't ask to speak to, I just hang up. Okay? I don't waste my time. I don't waste their time. I just hang up. And I think increasingly that's a common behavior. I think people get so flooded with so many nuisance calls that even otherwise very polite little old ladies just hang up the phone. In the U.S., very recently, in the 2016 presidential election, all of the polls were predicting that Hillary Clinton was going to win, when, in fact, as we all know, Donald Trump won. All right? And there have been many discussions about why that's the case. One fairly widespread belief, and I haven't actually investigated any deep studies about this, but one fairly widely held belief was that because Trump was sort of prone to paranoia and prone to claiming that the press couldn't be trusted and all this stuff, that when the press inquired of people, do you plan to vote for Donald Trump in the election? The suspicion is that a lot of people who voted for Trump answered that they were not going to vote for Trump as a way of intentionally misleading the people asking the questions. Which is understandable. I mean, in my case, as I said, if someone's trying to poll my opinion about something, I just hang up. But if I were in a worse mood, I might lie to them. Okay, and then your sample is really messed up. Also, 4 years later, in 2020, the polls were all suggesting that the Democratic Party was going to increase its majority in the House of Representatives, and that turned out to be false. Also, it turned out that although the Democrats did maintain a majority, their majority was slimmer than it had previously been. There's another famous case from way back in the 1950s in U.S. elections when Harry Truman was the Democratic candidate running against Dewey. I think the Republican candidate's name was Tom Dewey. And some newspaper decided that it really wanted to get a scoop. It really wanted to be, first to press with an announcement of who won the election. And so there's this famous photograph of Harry Truman holding up a newspaper announcing, "Dewey defeats Truman," which was wrong. Truman won the election, and won it, won it handily. And what everyone figured out after the fact was that in order to take this poll, the newspaper had called people on the phone and asked them who they were planning to vote for. Now, this was the 1950s. Only relatively wealthy people had phones. And so there was an implicit bias in this poll that the people in the poll were by mistake sampling from a population that was more wealthy than average. And it turned out that these more wealthy than average people were inclined to be Republicans. And so they thought they had, statistically valid results that Dewey was going to win. And it turned out that their sample was garbage. So that's something to be very, very, very careful about. That is an embarrassing mistake. Okay, things like political polls often lead to embarrassing mistakes. A much worse situation is if you are doing things like medical research or doing things like financial analysis, in which case you're not dealing with embarrassment. You're dealing with people's lives and you're dealing with people's life savings. And in situations like that, you'd really, really, really better be really careful that you're not going to kill people by accident or cause people to lose their life savings because of bad statistical analysis, which, unfortunately, both of those things happen all the time. All right. So be careful. Okay, I'm going to punt on these tests of understanding. We'll move on to our next topic.